Hi everyone. So I've come up with another video to demonstrate how to use internal timer of MSP430F5529, and we'll use that timer and generate the required timing. So let us take an example. So you can see here, so I want to blink an LED for every 1 second precisely. So let us understand the board. So you can see here I have connected LED to P1.0. I want to blink LED for every 1 second the precise time. So that means for 0.5 second it will be on, the next 0.5 second it will be off, and the next 0.5 second this LED will on. That means this LED will be on for every 1 second. Let us understand the board. So here is the board. So this is MSP430F5529. So you can see here the LED P connected to P1.0. Okay, this is the red LED. So I have connected that through USB. I have connected to the laptop. So this is the interfacing. Solution is, so LED is on for 0.5 second, LED is off for 0.5 second. That means this LED will on for every 1 second. So how to generate a 0.5 second timing? So I'm using TimerA0 of MSP430. I'll configure that in up mode, and I'm going to use the SM clock, and I'll divide that SM clock by 8. So all of you must know, when I power up microcontroller, that means when I switch on microcontroller, auxiliary clock will be around 32,768 Hz. Master clock will be around 1.4 megahertz, and also SM clock will be around 1.048 megahertz. That means when I switch on microcontroller, I'll be getting 1.48 megahertz in the SM clock. So that means we have F oscillator 1.48 megahertz. So since already I told I'm going to divide by 8, then the clock which I'm applying to the timer, the frequency is around 131 kilohertz. So therefore the time T is equal to 7.6 microsecond. That means for every 7.6 microsecond, timer 0 will increment by 1, and it start from 0 and go on incrementing towards FFFF. So I need to find, so if timer is incrementing for every 7.6 microsecond, if I increment how many times, I'll achieve 0.5 second. So here the relation 7.6 microsecond. If I increment how many number of times, it produces 0.5 second. So I'm going to find value of A equal to 0.5 second divided by 7.6 microsecond. So I'll get around 65,534. That means if I increment timer starting from 0 towards FFFF, if it reach the value FFFE, the time what I achieve, or timer, the timing it gives is 0.5 second. So let us see the program. So I'm disabling the watchdog timer. I'm using P1.0, therefore I'm configuring it as output, and I'm clearing the LED to begin with. So in the last slide I showed you how to calculate the value. The value I calculated for 0.5 second, so that is loaded to CCR register. Now I'm enabling CCR0 interrupt, and in the previous slide I explained I'm going to select SM clock configured in the timer configured in up mode, and the clock SM clock is divided by 8, and Next one is I'm clearing the timer register. In the next step, I'm enabling the global interrupt. So if I set the GI bit in SR register, so that will allow all the interrupts to reach CPU and interrupt. So once I enable GIE, all the interrupts by setting GIE, I am executing while 1 followed by semicolon. That means I am executing this instruction infinitely. But since by clearing TACLR register, by setting TACLR register, I am clearing a timer register. That means I am starting timer. Timer is keep incrementing by 1 for every 7.6 microsecond. So once a timer reaches FFFE, the time elapsed is 0.5 second, and it causes matching with the CCR0 register. So whenever a timer matches with CCR0 register content, there is an interrupt. So program control transfer from this to here. So I have declared a timer 0 A0 interrupt using hash pragma, and I have written function blink LED timer. Inside that I am toggling the LED connected to P1.0. That means whenever I come to ISR, I'll toggle the LED and goes back. So wait for another 0.5 second and come back here, come to the interrupt service routine and again toggle. Go back, wait for 0.5 second and come back. So this is how it works. Let me show the program. I will download it. So this is the program. I'll save this and build this, and let us download the program. Now currently the LED is off. You can see here, currently the LED is off, and if I download, so it's getting downloaded. So now you can see on the board the LED blinking for every 1 second. That means LED is on for every 1 second. This is the precise 1 second timing. LED is on for 0.5 second, LED is off for 0.5 second. So let us go back to the program and make some change. So instead of 65,535, so let us reduce this to half. It is nothing but 32,767. So change that, 32,767. So that means this value will blink LED for every 0.5 second. So there LED was blinking for every 1 second if it is 65,535. Now I have changed that to half, right? 32,767. Now LED will blink for every 0.5 second. Okay. So let us save this, build and download. So program got downloaded. Let us go back to the board. You can see now LED is blinking faster compared to the previous time. That means it is blinking for every 0.5 second. It is 0.25 second on, 0.25 second off. So this is how we can use timer to generate precise timing required. I hope you enjoyed this video. Thank you very much.